Alrighty, this will be our first problem for chapter 5. So Tom, who is a gymnast whose mass is 60 kilograms, holds an iron cross position in the rings. In this position, Tom's arms are abducted 90% or 90 degrees, and his trunk and legs are vertical. The horizontal distance from each ring to Tom's closest shoulder is 0.60 meters. Tom is in static equilibrium. So part A wants us to find the vertical reaction force that each ring exerts on each hand. So I drew a little picture here. It's not the best, but this gives you a pretty good idea of what we're looking like. So here's Tom. So that's the 90-degree angle that he's abducted at. And then here's a distance from each ring. So the distance from each ring does not matter at this point. So for this, we just want to know how much force is each ring exerting on his hand. So I believe the easiest way to do this is to find out how much force he's exerting total. So in other words, we're going to find his weight. So weight, kilograms, mass times gravity rather. Kilograms is our unit. So we've got 60 kilograms times 9.81. Just 588.6 newtons. So that's how much he's pulling down on the rings with. So to even that out, if he's in static equilibrium, the rings have to be pushing the exact same amount upwards. But this is his total. We want each hand on each ring. So we're just going to divide that by 2, which is going to give us 294.3 newtons. And that is how you solve part A. All right, so part B. So we're going to be finding the torque that is exerted by the right ring about Tom's shoulder joint. So our equation we're going to use is this right here. So torque is equal to force, and then R is our moment arm. So it gave us everything we need. Well, rather, it gave us our R. So our R is going to be this 0.6 meters. And then our force is going to be that 294.3 from last, because that is how much force it is putting on his hand. So 294.3 times 0.60. So our torque is 176.58. I guess Newton meters, I believe. But that's newtons, that's and meters. It'd be Newton meters. So that's part B. So for part C, we're looking for how much torque Tom's right shoulder adductor muscles must produce to maintain this position. So we just said, so here's Tom's shoulder, here's the ring, that's the ring, so here's Tom's hand. So we just said that this ring is exerting around 177 Newton meters of torque on his shoulder. So if you remember from the beginning of the problem, they state that Tom is in static equilibrium, as in he's just hanging there, he's not moving, nothing's changing. So in order for him to be in static equilibrium, the torque that his right shoulder adductor muscles are producing has to be equal to what the ring is exerting on them. So knowing that, it's going to be that 176.8 Newton meters as well. And that's part C. So then for part D, if the moment arm of Tom's right shoulder adductor muscles about a shoulder joint is 5 centimeters, how much force must these muscles produce for Tom to hold the iron cross? So, using this formula, we looking for torque for force. We know our torque is 176.58 Newton meters. Looking for this, and then it gave us our moment arm in centimeters, which we want in meters. Hundred centimeters and 1 meter, so 5 centimeters is equivalent to meters. Do some rearranging. Our meters will cancel. So the force his muscles must produce in order for him to hold the iron cross be around 3,531.6 newtons. And that is our first problem.